Welcome to the world of subatomic particles. Atoms, the basic units of matter, are made up of smaller particles called subatomic particles. The main ones are protons, neutrons, and electrons. Protons have a positive charge, neutrons have no charge, and electrons have a negative charge. There are also more exotic particles like quarks, which make up protons and neutrons, and neutrinos, which are incredibly light and neutral. By understanding these particles, we can unlock the mysteries of the universe, from the behavior of elements to the forces that govern their interactions. What are subatomic particles? Atoms consist of protons, neutrons, and electrons. Protons are positively charged, electrons are negatively charged, and neutrons have no charge. Electrons are much smaller, about 1/1800th the mass of a proton or neutron. These particles interact through fundamental forces: electromagnetic, strong, weak, and gravitational. Beyond these basics, subatomic particles also include quarks, which combine to form protons and neutrons, and neutrinos, which rarely interact with matter. Understanding these particles is crucial for studying chemistry, physics, and the universe itself. The structure of an atom. An atom's nucleus, at its core, contains protons and neutrons, held together by the strong nuclear force. Surrounding this nucleus is a cloud of electrons, which occupy different energy levels or shells. The number of protons in the nucleus defines the element, known as the atomic number. For example, carbon has 6 protons. Neutrons add mass and stability to the nucleus. Electrons, much lighter, are key to chemical reactions and bonding. The arrangement of these particles determines an atom's properties and behavior. Let's talk about protons. Protons are positively charged particles found in the nucleus of an atom. Each proton is made up of 3 quarks, 2 up quarks and 1 down quark, held together by particles called gluons. The number of protons in an atom's nucleus, called the atomic number, determines the element. For example, hydrogen has 1 proton, while carbon has 6. Protons also contribute to the mass of an atom and influence its chemical properties. They play a crucial role in the identity and behavior of elements. Now, neutrons. Neutrons are neutral particles located in the nucleus of an atom, alongside protons. They consist of 1 up quark and 2 down quarks, bound together by gluons. Neutrons add to the atomic mass, but do not affect the electric charge. They help stabilize the nucleus by reducing the repulsive forces between positively charged protons. The number of neutrons can vary within atoms of the same element, leading to different isotopes. For instance, carbon-12 has 6 neutrons, while carbon-14 has 8. Neutrons are essential for nuclear stability and reactions. Now, the electron. Electrons are negatively charged particles that orbit the nucleus of an atom. They are much lighter than protons and neutrons, about 1/1800th of their mass. Electrons occupy energy levels or shells around the nucleus, and their arrangement in these shells determines an atom's chemical properties and reactions. When atoms gain or lose electrons, they form ions, which are essential for electricity and bonding. Electrons also exhibit both particle and wave behavior, a key concept in quantum mechanics. Their interactions are governed by the electromagnetic force. Quarks, the building blocks of protons and neutrons. Quarks are fundamental particles that combine to form protons and neutrons. There are 6 types, or flavors, of quarks: up, down, charm, strange, top, and bottom. Protons consist of 2 up quarks and 1 down quark, while neutrons consist of 1 up quark and 2 down quarks. Quarks are held together by gluons, particles that mediate the strong nuclear force. This force is incredibly powerful, binding quarks tightly together. Understanding quarks helps us delve deeper into the structure of matter and the forces at play within the atomic nucleus. The 6 types of quarks. Quarks come in 6 flavors: up, down, charm, strange, top, and bottom. Up and down quarks are the most common, making up protons and neutrons. Charm and strange quarks are heavier and found in high-energy processes, like those in particle accelerators. Top and bottom quarks are the heaviest and were discovered more recently. Each quark type has a corresponding antiquark. Quarks also have a property called color charge, related to the strong force. The interplay of these quark types and their interactions is fundamental to particle physics. Gluons, the force carriers. Gluons are elementary particles that act as the carriers of the strong nuclear force, binding quarks together to form protons, neutrons, and other hadrons. Unlike protons and neutrons, gluons have no mass and no electric charge. They carry the color charge, related to the strong force, constantly exchanging between quarks, which keeps quarks bound tightly. This exchange happens so rapidly that quarks cannot be isolated individually. Understanding gluons and their role in the strong force is crucial for studying the stability and interactions of atomic nuclei. The strong force. The strong nuclear force is one of the four fundamental forces of nature. It is the force that binds quarks together to form protons and neutrons and holds protons and neutrons together in the atomic nucleus. The strong force is incredibly powerful, much stronger than the electromagnetic force, but it acts over very short distances. It is mediated by particles called gluons, which are constantly exchanged between quarks. This force is essential for the stability of atoms and the matter that makes up our universe. Understanding the strong force helps us comprehend nuclear reactions and the behavior of subatomic particles. The electromagnetic force. The electromagnetic force is one of the four fundamental forces of nature. It affects particles with electric charge, like protons and electrons. This force is responsible for electricity, magnetism, and light. Unlike the strong force, the electromagnetic force acts over long distances. It is mediated by photons, the particles of light. This force not only holds electrons in their orbits around the nucleus, but also governs how atoms bond to form molecules. Understanding the electromagnetic force is crucial for technologies like electronics and for explaining many physical phenomena. The weak force. The weak nuclear force is responsible for radioactive decay and certain types of nuclear reactions. It affects all fermions, which include quarks and leptons. The weak force is mediated by three particles, the W+, W-, and Z bosons. Unlike the strong and electromagnetic forces, the weak force acts over extremely short distances. It plays a crucial role in processes like beta decay, where a neutron transforms into a proton, an electron, and an antineutrino. Understanding the weak force is key for studying particle interactions and the behavior of subatomic particles. The gravitational force. Gravity is the weakest of the four fundamental forces, but acts over the longest distances, affecting all particles with mass. While it has a negligible effect on subatomic particles compared to other forces, it dominates at larger scales, governing the motion of planets, stars, and galaxies. The theoretical particle mediating gravity is the graviton, though it hasn't been observed yet. Understanding gravity is essential for studying the structure and evolution of the universe, despite its limited role in the behavior of subatomic particles. Antiparticles, the opposites. For every particle, there's an antiparticle with the same mass but opposite charge. For example, the positron is the antiparticle of the electron with a positive charge. When particles and antiparticles meet, they annihilate each other, releasing energy. This process is essential in particle physics and cosmology. Antiparticles are produced in high-energy processes, like those in particle accelerators. Understanding antiparticles helps us explore the fundamental symmetries of nature and the origins of the universe. Positrons, the anti-electron. Positrons are the antiparticles of electrons. They have the same mass as electrons, but carry a positive charge. Positrons are produced in certain types of radioactive decay and in high-energy processes like those in particle accelerators. When a positron meets an electron, they annihilate each other, producing gamma-ray photons. This process is used in medical imaging techniques like positron emission tomography, PET, scans. Understanding positrons is crucial for studying antimatter and its applications in science and medicine. Antiprotons and antineutrons. Antiprotons are the antiparticles of protons, having the same mass but a negative charge. Antineutrons are the antiparticles of neutrons, with the same mass and no charge, but opposite baryon number. Antiprotons and antineutrons are produced in high-energy collisions, such as those in particle accelerators. When they meet their corresponding particles, they annihilate each other, releasing energy. Studying these antiparticles helps scientists understand the symmetry of matter and antimatter in the universe and investigate why our universe is dominated by matter. Neutrinos, the ghost particles. Neutrinos are incredibly light, neutral particles that interact very weakly with matter, hence the nickname ghost particles. There are three types of neutrinos: electron, muon, and tau neutrinos, each associated with a corresponding lepton. Neutrinos are produced in nuclear reactions, such as those in the sun, stars, and nuclear reactors. Despite their elusive nature, billions of neutrinos pass through your body every second without any effect. Understanding neutrinos is crucial for studying fundamental particle interactions and the processes occurring in the universe. Types of neutrinos. There are three types, or flavors, of neutrinos: electron neutrinos, muon neutrinos, and tau neutrinos. Each type is associated with a corresponding charged lepton, the electron, muon, and tau, respectively. Neutrinos can change from one flavor to another through a process called neutrino oscillation, a phenomenon that provides evidence for neutrino mass. Detecting and studying these flavors and their oscillations help scientists explore the fundamental properties of neutrinos and understand their role in the universe. Neutrino oscillation. Neutrino oscillation is the process by which a neutrino changes from one type, or flavor, to another as it travels. This phenomenon occurs because neutrinos have a tiny mass and the different flavors are quantum superpositions of three mass states. Neutrino oscillation was first confirmed in experiments detecting solar neutrinos and atmospheric neutrinos. This discovery has profound implications for particle physics, indicating that the standard model needs modifications to account for neutrino mass. Understanding neutrino oscillation helps scientists delve deeper into the nature of neutrinos and their role in the universe. The Higgs boson. The Higgs boson is a fundamental particle associated with the Higgs field, which gives mass to other particles. Predicted by the Standard Model of Particle Physics, the Higgs boson was discovered in 2012 at CERN's Large Hadron Collider. The Higgs field permeates the universe, and particles acquire mass through their interaction with this field. The discovery of the Higgs boson confirmed this mechanism, providing crucial insight into why particles have mass. Understanding the Higgs boson and its field is essential for comprehending the fundamental structure of matter. The Standard Model of Particle Physics. The Standard Model is a theory that describes the fundamental particles and forces of the universe, except gravity. It includes particles like quarks, leptons, and bosons, which mediate the forces. Quarks combine to form protons and neutrons, while leptons include electrons and neutrinos. The force-carrying bosons are the photon, electromagnetic force, gluons, strong force, W and Z bosons, weak force, and the Higgs boson. This model has been incredibly successful in explaining and predicting particle behavior, but still leaves questions unanswered, such as the nature of dark matter. The four fundamental forces. There are four fundamental forces that govern the interactions of particles in the universe. The gravitational force affects objects with mass, acting over long distances. The electromagnetic force affects charged particles, responsible for electricity and magnetism. The strong nuclear force binds quarks together in protons and neutrons, acting over very short distances. The weak nuclear force is responsible for radioactive decay and neutrino interactions. Each force is mediated by its own set of particles, and together, they shape the behavior of matter and energy. Particle accelerators. Particle accelerators are machines that speed up charged particles to high energies and then smash them together. This allows scientists to study the fundamental components of matter and the forces between them. The Large Hadron Collider, LHC, at CERN is the most powerful accelerator, where the Higgs boson was discovered. These collisions recreate conditions similar to those just after the Big Bang, helping scientists explore the origins of the universe, the nature of particles, and potential new physics beyond the Standard Model. Particle detectors. Particle detectors are devices used to observe and measure the properties of particles produced in accelerators or cosmic events. Detectors like the ones at the LHC are composed of various layers, each designed to detect different types of particles and interactions. They can measure energy, momentum, charge, and other properties. Detectors are crucial for experiments in particle physics, enabling discoveries like the Higgs boson and insights into the behavior of subatomic particles. Understanding how detectors work is essential for interpreting experimental data in physics. Cosmic rays. Cosmic rays are high-energy particles from outer space that constantly bombard Earth. They consist mostly of protons and atomic nuclei, but also include electrons and gamma rays. When cosmic rays collide with the Earth's atmosphere, they produce showers of secondary particles. Studying cosmic rays helps scientists understand high-energy processes in the universe, such as supernovae and black holes. Cosmic rays also provide insights into particle interactions at energies higher than those achievable in accelerators, offering a unique perspective on fundamental physics. Dark matter. Dark matter is a mysterious substance that makes up about 27% of the universe. Unlike ordinary matter, it doesn't emit, absorb, or reflect light, making it invisible and detectable only through its gravitational effects. Dark matter explains the missing mass in galaxies and clusters, influencing their rotation and structure. Scientists hypothesize that dark matter consists of unknown particles, potentially detected in the future by advanced experiments. Understanding dark matter is crucial for uncovering the full composition and behavior of the universe. Dark energy. Dark energy is an unknown form of energy that makes up about 68% of the universe and is responsible for its accelerated expansion. Discovered through observations of distant supernovae and the cosmic microwave background, dark energy works against gravity, pushing galaxies apart. Its exact nature remains one of the biggest mysteries in cosmology. Some theories suggest it could be related to the vacuum energy of space or modifications to gravity. Understanding dark energy is vital for explaining the universe's fate and its large-scale structure. The Big Bang Theory. The Big Bang Theory is the leading explanation for the origin of the universe. It proposes that the universe began about 13.8 billion years ago from an extremely hot, dense state and has been expanding ever since. Evidence supporting this theory includes the cosmic microwave background radiation, the abundance of light elements, and the redshift of galaxies. The theory provides a framework for understanding the evolution of the universe, from the formation of particles and atoms to galaxies and large-scale structures. Studying the Big Bang helps us explore the universe's beginnings and its ultimate fate. The role of symmetry in physics. Symmetry plays a crucial role in physics, governing the laws and behaviors of particles and forces. Symmetries lead to conservation laws, such as the conservation of energy, momentum, and charge. For instance, rotational symmetry leads to angular momentum conservation. In particle physics, gauge symmetries underpin the interactions described by the Standard Model. Symmetry breaking can lead to phenomena like the Higgs mechanism, giving particles mass. Understanding symmetry helps physicists develop theories and models that describe the fundamental workings of the universe. Quantum mechanics. Quantum mechanics is the branch of physics that deals with the behavior of particles on very small scales, such as atoms and subatomic particles. It introduces concepts like wave-particle duality, where particles exhibit both wave-like and particle-like properties, and quantization, where certain properties take on discrete values. Key principles include Heisenberg's uncertainty principle, which states that certain pairs of properties cannot be simultaneously known to arbitrary precision, and Schrödinger's equation, which describes how quantum states evolve. Quantum mechanics is essential for understanding the microscopic world and has led to technologies like semiconductors and quantum computing. Quantum entanglement. Quantum entanglement is a phenomenon where particles become interconnected, such that the state of one instantly influences the state of another, regardless of distance. This spooky action at a distance, as Einstein called it, has been experimentally confirmed. Entangled particles share a quantum state, and measuring one instantly determines the state of the other. Entanglement is crucial for quantum computing and cryptography, enabling secure communication and powerful computations. Understanding entanglement helps us explore the non-local nature of quantum mechanics and potential applications in technology. The Heisenberg uncertainty principle. The Heisenberg uncertainty principle is a fundamental concept in quantum mechanics stating that certain pairs of properties, like position and momentum, cannot be simultaneously measured with arbitrary precision. The more precisely one property is known, the less precisely the other can be known. This principle reflects the inherent limitations in measuring quantum systems and arises from the wave-like nature of particles. It challenges classical intuitions about measurement and determinism, highlighting the probabilistic nature of quantum mechanics and influencing how we understand and interact with the quantum world. Wave-particle duality. Wave-particle duality is the concept that particles, such as electrons and photons, exhibit both wave-like and particle-like properties. This duality was first observed in experiments like the double-slit experiment, where particles create interference patterns characteristic of waves. Conversely, particles also show discrete interactions, like collisions, typical of classical particles. This duality is a cornerstone of quantum mechanics, demonstrating that particles cannot be described solely as waves or particles. Understanding wave-particle duality helps us grasp the complex behavior of subatomic particles and the nature of quantum phenomena. Schrödinger's equation is a fundamental equation in quantum mechanics that describes how the quantum state of a system evolves over time. It's a wave equation that predicts the behavior of particles at the quantum level. The equation's solutions, called wave functions, contain all the information about a particle's state, including its position and momentum probabilities. Schrödinger's equation provides a framework for understanding the dynamics of quantum systems and is essential for predicting the outcomes of quantum experiments and phenomena, shaping our understanding of the microscopic world. The Pauli exclusion principle. The Pauli exclusion principle states that no two fermions, particles like electrons, can occupy the same quantum state simultaneously within a quantum system. Proposed by Wolfgang Pauli, this principle explains the structure of the periodic table and the behavior of electrons in atoms. It leads to the arrangement of electrons in distinct energy levels and orbitals, preventing them from collapsing into the same state. The exclusion principle is fundamental to understanding the stability and diversity of matter, influencing atomic structure, chemical properties, and the formation of complex systems. Fermions and bosons. Subatomic particles are categorized into two groups, fermions and bosons. Fermions, like quarks and leptons, make up matter. They obey the Pauli exclusion principle, meaning no two fermions can occupy the same quantum state. Bosons, like photons, gluons, and the Higgs boson, are force carriers and do not obey this principle, allowing them to occupy the same state. This distinction explains why matter has structure and stability, while forces can be transmitted through fields. Understanding fermions and bosons is key to grasping the fundamental nature of particles and forces. Leptons, the lighter particles. Leptons are a family of fundamental particles that do not experience the strong force. There are 6 types: the electron, muon, tau, and their corresponding neutrinos. Electrons are crucial for forming atoms, while muons and taus are heavier and unstable, appearing only in high-energy processes. Neutrinos, as discussed earlier, are nearly massless and interact weakly with matter. Leptons play a vital role in various interactions and processes, from electricity to beta decay, making them essential for understanding particle physics. Muons and taus. Muons and taus are heavier relatives of the electron, belonging to the lepton family. Muons are about 200 times heavier than electrons, while taus are about 3,500 times heavier. Both are unstable and decay into lighter particles. Muons are produced in cosmic rays and particle collisions, while taus are seen in high-energy environments. Despite their short lifespans, studying muons and taus helps scientists test the Standard Model and explore new physics beyond it. They provide insights into fundamental forces and particle interactions. The role of symmetry breaking. Symmetry breaking is a phenomenon where a symmetric system ends up in an asymmetric state. In particle physics, it explains how particles acquire different properties and masses. The most famous example is the Higgs mechanism, where the Higgs field breaks electroweak symmetry, giving mass to W and Z bosons while leaving the photon massless. Symmetry breaking is crucial for understanding the diversity of particles and the structure of the universe. It provides insights into phase transitions and the evolution of the early universe. The Large Hadron Collider, LHC. The LHC is the world's most powerful particle accelerator, located at CERN. It accelerates protons to near-light speeds and collides them, recreating conditions similar to those just after the Big Bang. The LHC's detectors observe the resulting particle interactions, leading to discoveries like the Higgs boson in 2012. Researchers at the LHC study fundamental forces, search for new particles, and explore the limits of the Standard Model. The LHC is crucial for advancing our understanding of particle physics and the universe. Supersymmetry, SUSY. Supersymmetry, or SUSY, is a theoretical framework proposing that every particle has a superpartner with different spin properties. For example, fermions like electrons would have bosonic superpartners called selectrons. SUSY aims to resolve issues in the Standard Model, such as the hierarchy problem, and provide candidates for dark matter. While no superpartners have been discovered yet, experiments at the LHC and other facilities continue to search for evidence. Understanding SUSY could revolutionize our knowledge of particle physics and the fundamental forces of nature. String theory. String theory is a theoretical framework suggesting that the fundamental particles are not point-like, but instead tiny, vibrating strings. Different vibration modes correspond to different particles. String theory attempts to unify all fundamental forces, including gravity, into a single framework. It requires additional dimensions beyond the familiar 4, 3 space, and 1 time to be consistent. While it remains unproven, string theory provides a compelling approach to understanding the universe's deepest mysteries and the connections between quantum mechanics and general relativity. Quantum field theory, QFT. Quantum field theory is the theoretical framework combining classical field theory, quantum mechanics, and special relativity. It describes how particles interact and are created and annihilated. In QFT, particles are excitations of underlying fields that permeate space. For example, photons are excitations of the electromagnetic field. QFT underpins the Standard Model, explaining particle interactions through exchanges of force-carrying bosons. Understanding QFT is essential for comprehending the behavior of particles at high energies and the fundamental forces shaping our universe. Quantum chromodynamics, QCD. Quantum chromodynamics is the theory describing the strong nuclear force, which binds quarks together to form protons, neutrons, and other hadrons. In QCD, quarks interact by exchanging gluons, the force carriers of the strong force. Quarks possess a property called color charge, and gluons mediate the interactions between these color charges. The force is incredibly strong, preventing quarks from being isolated, a phenomenon known as confinement. Understanding QCD is crucial for studying the structure of atomic nuclei and the interactions of subatomic particles. The electroweak theory. The electroweak theory unifies the electromagnetic and weak forces into a single theoretical framework. Proposed by Sheldon Glashow, Abdus Salam, and Steven Weinberg, it describes how these forces operate at high energies. The theory introduces the W and Z bosons as mediators of the weak force and the photon for the electromagnetic force. The Higgs mechanism breaks the electroweak symmetry, giving mass to the W and Z bosons while leaving the photon massless. The electroweak theory is a crucial part of the Standard Model, explaining interactions fundamental to particle physics. The role of the Higgs field. The Higgs field is a fundamental field permeating the universe, associated with the Higgs boson. Particles acquire mass through their interactions with the Higgs field. Without it, particles would remain massless, preventing the formation of atoms, and, consequently, matter as we know it. The Higgs field explains why some particles, like the W and Z bosons, have mass, while others, like photons, do not. Understanding the Higgs field is essential for comprehending the mechanism that gives mass to elementary particles and shapes the universe's structure. Grand unified theories, GUTS. Grand unified theories aim to merge the three fundamental forces of the Standard Model, the electromagnetic, weak, and strong forces, into a single theoretical framework. GUTS suggests that at extremely high energies, these forces unify, becoming indistinguishable. This unification could provide insights into the early universe and the relationships between different forces. While GUTS have yet to be experimentally confirmed, they guide research in particle physics, suggesting new particles and phenomena. Understanding GUTS could lead to a deeper, more unified picture of the fundamental forces. The search for new physics. While the Standard Model explains much about the subatomic world, it leaves many questions unanswered, such as the nature of dark matter and the imbalance between matter and antimatter. Physicists search for new physics beyond the Standard Model to address these mysteries. Experiments at particle accelerators, such as the LHC, look for signs of new particles, forces, and interactions. Theories like supersymmetry, extra dimensions, and string theory offer potential answers. Understanding new physics could revolutionize our knowledge of the universe and its fundamental components. Particle physics and cosmology. Particle physics and cosmology are interconnected fields that explore the universe's smallest and largest scales. Particle physics studies the fundamental particles and forces, while cosmology examines the universe's origin, structure, and evolution. Discoveries in particle physics, like the Higgs boson, provide insights into cosmological phenomena, such as the early universe and cosmic inflation. Conversely, cosmological observations, like the cosmic microwave background, inform particle physics theories. Understanding the synergy between these fields helps us explore the universe's fundamental nature and its ultimate fate. The future of particle physics. The future of particle physics holds exciting possibilities, with new experiments and technologies on the horizon. Next-generation particle accelerators, such as the proposed Future Circular Collider, aim to explore higher energy scales and search for new physics beyond the Standard Model. Advances in detector technology and computational methods will enhance our ability to study particle interactions and rare phenomena. International collaborations and multidisciplinary approaches will drive discoveries, deepening our understanding of the universe's fundamental components and forces. The future of particle physics promises to unveil new mysteries and expand our knowledge of the cosmos.